Hello, everyone, and welcome to Algorithms Live. This week we have a special guest, which is David Harmeyer. We're going to talk about his problem string concatenation from the Facebook Hacker Cup. So, David, thanks for coming on the show and talk about your problem.
Good morning, Matt. I'm glad to be here. As you know, I'm a huge fan of the show, so I'm very excited about this episode.
Yeah, it should be a lot of fun, and we have a pretty good problem prepared that you prepared for Hacker Cup. If you don't know David's handle, it's second thread, which was sneakily added to the problem statement for Facebook Hacker Cup, so it didn't really disguise very well who wrote this problem. Um, okay, so let's dive right into the problem. So David, do you want to start talking about what the problem is asking?
Sure. So, although the problem is called string concatenation, this caught several contestants off guard, so I want to clarify right away. It's not actually about the strings that most people traditionally think of in computer science. Like, it's not about a bunch of characters in a row. It's actually about a bunch of pieces of yarn. And you have these all over your apartment and you want to clean them up. So in particular, you have n strings, where each string has an integer length between 1 and 200,000. And you're going to clean up these strings by combining them into a thread by fusing their ends together. And you want to make two threads. One thread you'll store on your first spool and another thread for a second spool. And this will allow you to reuse all of these pieces of string. But then you might not be able to, or you might not want to use all of the pieces of string, so you can throw away some pieces of string. In particular, you can throw away up to k pieces of string. But you have this interesting constraint, which is you want your two threads to be exactly the same length. And then there's some interesting bounds on k in particular. So on the number of threads you can throw away, there are some restrictions on that. It's not just an arbitrary number. So the bounds on k are you're allowed to throw away up to the min, well, up to k, where k goes between the min of n minus 2 and 25. That's the lower bound for k, and then the upper bound is always n minus 2. So k can vary, and k is the number of pieces you can throw away. And kind of this is a bit tricky of a bound, but one way of interpreting this is you're never allowed to throw away all of the string. That's why it's bounded by n minus 2. But you always are allowed to throw away up to 25 pieces, where 25 is it can be smaller if n is really small, but if n is really big, k will always be at least 25.
Okay, so then the 25 bound gives you just a lot of leeway in terms of what you can throw away, instead of having to use all the string at a given time.
It'd be a really tricky problem if you weren't allowed to throw away anything, or if you could throw away everything but maybe one piece, then it'd be a really hard problem to solve.
Yeah.
But here we've got a good amount of freedom, which maybe indicates that it's more feasible of a thing to solve when we have lots of pieces of string.
Yeah, so I guess the first thing to note when we look at this problem is that k equals 0 case is a pretty famous NP complete problem called the partition problem.
Yeah, so I guess if people aren't familiar with that, I think the idea is you have a bunch of integers and then you want to put them into two sets with exactly the same sum.
Right, and so you can just think of this problem as instead of integers, it's these strings to give it kind of this flavor text, where the strings are not character strings, but actually yarn. So.
Yeah, and then this is famously there's not really a cleaner way of doing it than the DP or some 2 to the n solution.
Right,
so
right.
It's very difficult.
Yeah, if the strings can be arbitrary length and size, then we can't do it very efficiently. One of the things that always catches my eye with partition problem is it has a lot of really tight approximation algorithms. So you can get pretty close to the optimal solution, but not get the optimal solution. So I think what makes this problem really interesting so far is we want the optimal solution. We want to find a partition if one exists, and if one does not exist, we need to be able to say so. So we're going to be solving it in the exact case, but this k-bound, which is a really interesting k-bound, is the piece that's going to give us this leeway and not have to deal with this NP-complete problem.
And then I guess just something to mention before we move on too much is the thing that you actually print is you have to print what this partition is. So what strings are in the first thread, what strings are in the second thread, and then everything else you'll throw away. Not just whether it's possible or not. So you have to determine whether it's possible, but also how do you do it.
Yeah, and so if it's not possible, you just like state it's not possible. If it is possible, you actually have to print the partition and show that you can do it. So it is constructive as well as being not just a decision variant. Okay, I guess what we can do is we can dive right in. The bounds for the number of strings are up to 2 to the times 10 to the fifth. So David, what's your solution idea for doing this kind of problem?
Huh. Well, that's a little bit scary of some bounds, Matt. So what do you say we delete the multiplication sign and the 1 and the 0 and just leave with the n less than or equal to 25? That might be a bit more approachable.
Yeah, this looks a little less scary. So I guess we can dive into this a little bit simpler problem and see where we can get.
So I guess the first thing we should probably mention is there is a solution that would work if n were even smaller. So if n went down to maybe like 12 or 13, then we could do a 3 to the n approach because we know that each string is either going to be part of the first thread or the second thread, or it's going to get thrown away. And if we know that for each string, we can just check whether some combination of zeros, ones, and twos will work. In particular, if the sum for the first string or the first thread will be equal to the sum for the second thread.
Ah, okay. So then we can just at every single space do one of the three options for our choices and construct two disjoint sets that are completely separate that sum to the same thing, just brute force style.
Yeah, we can just check all of them. But obviously the solution isn't going to work for much bigger n, and we'll kind of let it die here because it's not very useful. But we can talk about something separate which will work for a little bit bigger bounds, yeah, and up to 25. And in this case, we can imagine if we put the problem on hold for a minute, and instead of trying to find two groups that are disjoint with the same sum, if we try and just find two different subsets that differ in some way but have exactly the same sum, we can do a 2 to the n dp. So we can try every submask and then say for this submask, what is the sum over all of its elements?
Ah, I see. So you're just relaxing the constraint on the problem so that you can have overlapping choices. And now we just want two strings that sum to the same length, but they don't both take everything and they both don't delete everything.
Yeah, it's okay if one of them takes everything because like that means if the other one's different, that means there would be like a 0 in there, and we know that's not going to be the case. So we don't really have to worry about any of those additional edge cases really. We just want to find two different subsets with exactly the same sum.
So they have to differ in at least one thread, is what you're saying.
Yeah, exactly.
Okay.
And what you just highlighted actually kind of shows us an interesting way of adapting a solution to this easier problem to a harder problem. So basically, since we know they'll differ in at least one place, we can look at all of the places they differ. And it turns out that since the blue thread here has the same sum as the red thread here, we can remove this from both of them, and then they'll still have the same sum because we subtracted the same amount.
Yeah, so we're basically just counting this twice, so we know that this whole red box sums to the same thing. So we can just remove this piece entirely from our solution, and now we've constructed from our overlapping subsets two subsets that are disjoint.
Exactly. So yeah, we could just like do a 2 to the n dp and say for each submask, find its sum and store that somewhere in an array. And if we ever have two different submasks that map to the same sum, we can say, okay, from these two, these might have some overlap. But if they do, we can remove that overlap and then find two disjoint subsets, which will solve the problem when n is really big. All right. So yeah, that'll solve the problem when n's up to 25. But we have quite a ways to go here. We got to go all the way up to 200,000. So this is going to be a bit tricky. Maybe the next thing we can do is say, when n is 25, what are the odds that we find a solution?
So what you're saying is pick a random pair of pairs. So pick a subset on one side, pick a subset on the other side. What's the probability that they're two equal substrings?
Maybe, but maybe more in particular, if we look at like all of the substrings that exist, or all of the subsets that exist, what's the chance that two different subsets have the same sum?
So what you're saying is, let's forget about the two different strings. Let's just focus on one string, construct all of the possible cases by just sampling randomly from the set of all subsets. And then what's the odds that we'll end up with two separate subsets that sum to the same thing, because we can just make one of them the blue string and then put the two things together.
Exactly, yeah. If we can find one of these, we know there is a solution. So we want to say, like, is there always a solution maybe, or is the solution going to exist most of the time, or is it easy to construct a case where there isn't a solution when n is big? And like a common example of something that might help us here is like the pigeonhole principle, which I'm sure you've described before. So we might want to ask ourselves, how many subsets are there? And then how many spots are there that these subsets could occupy?
And so, so what are your pigeons and what are your pigeonholes in this case?
So in this case, a pigeonhole would be some sum. So every subset has some sum. And if you ever have two different subsets that map to the same sum, you're going to find a solution. You can remove the overlap, and now you have two disjoint subsets with the same sum. And then your pigeons are the subsets.
The pigeons are the subsets themselves. And so how many holes can we have up to in this problem?
Well, the length of each string is up to 200,000. And since you have at most 25 strings here, the biggest possible sum is going to be 25 times 200,000. And then the other question is, like, how many pigeons do we have to worry about? And for that, we have 25 spots. So there are, each spot we can either include or not include in a subset. So there are 2 to the 25 different subsets. And let's do the math here to see what that number is. So 2 to the 25 is 33 million. And then 25 times 2 times 10 to the 5th is about 5 million.
So we have 5 million pigeonholes and 33 million pigeons. So there has to be at least 2 pigeons and pigeonhole. And then if we're doing it by sampling, then it'll even collide faster than that by probability, as a kind of a birthday paradox thing.
Yeah, so it turns out we can probably find a solution most of the time with like much fewer than 25 elements. But even in the worst case, we know no matter what happens, even if the odds are stacked against us and the universe wants us to fail, we know we are going to find a solution if we have 25 things. So this solution will definitely work eventually if we have sufficiently many elements, which is very helpful because now we know that if we're given 25 things and we can find a solution, we might be able to use that to help solve the problem with bigger bounds. So I guess maybe now we should consider a solution possibly with up to 50 elements. So obviously we can't do a 2 to the 50 here. That'd be too tricky. But we have this idea, we have maybe a little bit of a black box where we can say, if you give me 25 elements, I can do the 2 to the n solution that we talked about last time, and I can give you back 2 threads with the same length that use some of those strings.
So what you're saying is only look at the first 25 strings?
Yeah, that's one thing we could definitely do. And then if we have that, we can come up with some solution that uses some of those strings. And then we have like 2 threads, which maybe we can build off with the remaining elements.
Okay, so you have 25 strings up front. So you're saying for the first 25 strings, we solve the problem by constructing our red and blue string. And now we have something to build off of for the remaining string.
Yeah, so you can imagine if we have like 2 threads of equal length in the first half and 2 threads of equal length in the second half, we can like join the first 2 together and then we have just like one solution by combining those 2 halves.
So, but what about crossing the boundary here? So if you ended up having something that summed to, let's say, like 30 and 15 over here, and then you just reverse it, so your red thread and your blue thread are kind of opposite. So they both sum to 45 across both strings. And so the reason we don't have to consider this case is because we're guaranteed that there is a solution on this side by the pigeonhole principle, and there's guaranteed there is a solution on this side by the pigeonhole principle. So even though this case exists and we could construct something this way, we don't have to worry about it because we have this guarantee from pigeonhole principle, right?
Yeah, exactly. That's a good thing to point out for sure. The other thing we have to be a little careful with, though, is although this will give us a solution, the solution might not be valid. So in this case, we might throw away up to 23 strings from the left and up to 23 strings from the right. But we might not be allowed to throw away 46 strings in total. We only are guaranteed that we're allowed to throw away 25. So we have to be a little bit careful with that, and we have to adapt our solution accordingly, because all we're doing is finding some solution on the left and some solution on the right, but when we're done, we might throw away a whole bunch of strings. Mm-hmm. Does that kind of make sense?
Yeah, and you only have that budget of 25 strings, so this is lower bounded by 25. And so part of the problem here is we could throw away too many things, because this is our leeway, which is a pretty big leeway, but we still need to take advantage of it somehow.
So one thing to keep in mind here is that in our initial solution, we were saying we can throw away as many as we want. We can throw away 23, we can throw away just 2, we might not even need to throw away any of them. But in this case, we can't give the full budget to both sides. So you might think like, well, what if there's some sort of like DP or whatever that we do to distribute this budget? But it gets really tricky, because once we start having these restrictions on how many you're allowed to throw away, that kind of removes our guarantee that a solution will exist. So if we give ourselves a really annoying constraint in the first half, and then all of a sudden, like, we can't have a solution, that doesn't necessarily mean that a solution doesn't exist. It just means a solution crosses the middle. So all of a sudden, this idea just kind of breaks. But instead, we can do kind of a different approach, which is we can, like, maybe recycle our garbage.
Okay. So you're thinking maybe we get our red and we get our blue together, and we say that these two are the equal length, but we want to be able to reuse stuff, so we just take this string and then put it over on the second side that we need to solve.
Exactly, yeah. So since we weren't using it earlier, we can just include it in a group, and as long as the group has at least 25 things in it, we can find some solution.
Okay, so it's kind of like almost like a queue. You're basically, or a sliding window even. You're basically grouping this with the first 24 elements of this to form your next group, and then we're guaranteed to find a solution here. But now we're also guaranteeing that we're not like throwing away too much, because we're at least considering the leftovers.
And we might still not use this leftmost thing in the next group. We might need to keep using it and some other elements in this other group for further groups, but we know we'll get rid of at least 2 elements.
Yeah, so we might even like use everything in this example, but then what we'll do is we'll just solve the last problem where this and this are paired together, something like that.
And we can keep doing this up until we have fewer than 25 things. Because once the group starts getting small, we might not have a solution anymore. But as long as there are at least 25 things, we can use the pigeonhole principle that we showed earlier to show that we will be able to decrease the size. Maybe we should talk about the runtime of this approach to see how big of an n this can support. So for each step, we do sort of a 2 to the n dp. And in each step, n is equal to roughly about 25. So it's going to be about 2 to the 25 times the number of times we run this.
Okay, so we don't know how many times we're running this DP, but we have 2 to the 25 DP that we can run to basically just find a solution that has the collision, and then we pull it off the front. And what we'll need to bound is like how many things are we throwing, or how big is our combined pair going to be, because that will limit the amount of things that move on to the next level.
Yeah, so you might think like we throw away 25 each time, but of course we don't. We might throw away just a couple each time. But we know there are at least 2, so we're always going to throw at least 2.
Right.
Which means our n runtime, if n is like 100, for instance, that means there are 75 things we need to throw away, or we need to end up using, and then throw away the last 25. And if we're going to use 75, each time we run this DP, we'll use at least 2 of them. So we run this DP about 75 over 2 times, and then times the 2 to the 25. So this approach works in the worst case runtime about up to n equals 100. Although in practice, we end up finding the answer a bit quicker than a full 2 to the n. So if we break out early, we can get it to work a bit faster. But I think this is probably the best we can easily prove for now.
So my question here is, if we're doing a kind of DP like this, is there any value in making the number of elements that you end up using in the DP as long as possible as a string?
What do you
Or
mean
is
by
the,
as long as possible?
so I mean, so you basically have to reconsider any string that you don't place in the blue group or the red group. And so in the DP, I was wondering if there, because right now the DP is just yes, no. Can I like form it
Hmm.
and then build back the solution from there? I was wondering if there was a way to do the DP where like there were costs of basically having the length of the string or the number of things that you take away is to be as large as possible to reduce the number of times that we end up having.
Ooh, that's a good idea. Yeah, that might be smart. You might be able to improve at least by some constant factor with that. Um, but I think one thing that might slow you down a bit with is if you're gonna do that, you have to run the full 2 to the n DP, right? If you want to find like the actual best answer, in particular the answer that throws away the most things. If you just look for any answer, then you can break out as soon as you find any two subsets with the same sum.
Okay, so like run the DP recursively as soon as you hit your base case that says yes, then return right away, and then you're not doing as much work.
Yeah, that might work. I'm not actually sure which one's faster. You could
Yeah.
do
So the only
some
the only
tests.
thing that would concern me about maybe going down that approach, just so we can talk about it, is you're also this approach, this DP approach, is going to construct the case that's overlapping. So if you maximize the length of both the strings in the DP, then we might have something where, like, oh, we found two solutions, but they just overlap so much that you're going to have to reconsider all these ones in the middle, right?
Yeah, that's true.
Yeah, so maybe that optimization is a little too eager because we end up having this case. But if somebody watching can think of something where this optimization ends up helping, like leave a comment in the video, and it would be really interesting to see.
It turns out empirically, you usually throw away about 10 things if you just break out early as soon as you find the first example, which is that's a pretty good constant factor. So usually instead of 75 over 2, you end up with about 75 over 10
Hmm.
in practice.
Okay. So we get like an empirical gain where it's really hard to make a case where you throw away exactly 75 over 2, and then you're also breaking all other kinds of solutions.
Yeah, and even if it is just 75 over 2, you can very easily make it 75 over 3 or over 4, just with a couple observations. Um, because if it's over 2, that means there's a pair of elements that are exactly the same, and that's really easy to find. You don't need a TP for that. Yeah, using this solution, we can actually solve it for n up to like roughly n equals 100, but we can't go much bigger than that, or at least we can't go much bigger than that and still be confident in our runtime
Hmm.
because things get a bit scary. This 2 to the 25, it seems like it might slow us down too much for bigger n. So yeah, let's kind of pivot to maybe a different approach. When n is equal to 100, or when n's equal to like 1,000 or something bigger than 100, something where our 100 approach wouldn't work. Let's say we randomly pick some binary string of length n. So this will give us like basically a way of representing some random bit mask. So every string, there's like a 50% chance that it's included in this bit mask. And if we do this, this will give us some sum. We can just figure this out in linear time, just iterating through all of the strings and then adding that number, so either the 1 or the 0 times its value. This will give us its sum. Now if we do this, we'll get some total, right? This will give us like some total length. Now the question is, like, what's the chance that a pair of these two random strings will have the same sum? Each string has some sum, and the value of the sum is gonna be between between 0 and 1,000 times 200,000, so 2 times 10 to the 8.
So it's n times the size of the lengths. So it's 2
Yeah, the
times
max length.
10 to the fifth. And in this case, we have 10 is 1,000. So this is 2 times 10 to the eighth.
So now the question is, like, let's say we just kept picking these random strings until we found some collision. How many strings are we going to need on average for there to be two different strings that have the same sum? And this is like very similar to the birthday paradox question, which is like how many people do you need in a room for there to be two different people with the same birthday? You might think it's really big, but in fact it's actually roughly like square root of 365, or in this case, square root of 2 times 10 to the 8. And that's because for like n things, you have n squared chances of two things matching.
Right. Because you're basically, you can think of it like you're creating a hash table almost with the sum. By picking these random strings, you're like almost like randomly hashing to a value. And then there aren't that many values that you can pick from. So it's very likely as you do this n times, it won't take too long before you collide with something that you've already placed in the table. And that's the idea with the birthday paradox, just as intuition. Although if anyone is interested in this idea, they can look up the birthday paradox as a principle. And the idea with the birthday paradox is just what's the probability that if we get a room of a number of people, that two people have the same birthday with high probability, given how many people are in the room. And it turns out it's pretty high because it's high probability that at least one of the pairs has a collision because there are just so many pairs. Exactly, n squared pairs, basically.
The n squared, that's where the square root's coming from.
Yep, exactly.
So let's say we just do this. Like the question is like, what does our runtime end up being? And it turns out like each iteration we have a random bit string of length n, and we have to find the sum. So that's a runtime of about 1,000, and we're going to have to do this about 1.4 times 10 to the 4 times. So our final runtime is going to be about 10 to the 7 in order to find a pair that works.
Mm-hmm.
Does that kind of make sense?
No.
No? Okay. All right. Sounds good. Thank you for letting me know. So we're going to pick a random bit string.
Mm-hmm.
And we're going to keep doing this until two bit strings have the same sum. So each bit string, like the number of bit strings we'll have to generate is square root of 2 times 10 to the 8.
Okay. So that's about, what is square root of 2 times 10 to the 8 about?
It's like 1.4 times 10 to the 4, but let's just say 10 to the 4.
Okay.
Yeah, so we're going to need to make 10 to the 4 strings. Mm-hmm. And the runtime of making one string is 10 to the 3.
Right, because you have to go through each element in the string, like once you pick the pairing and verify what its sum is.
Mm-hmm. So in total, our runtime for finding two different bit strings with the same sum is going to be 10 to the 7.
Okay.
So we'll just do this. And once we've done this, we can use our original idea that we first came up with the 2 to the n approach, which is if we have any overlap, we can remove the overlap that both strings share, and we can remove a whole bunch of bits here. So any bit that's in exactly one of the two strings, we can end up removing it, any of these strings. Mm-hmm. And on average, that'll be like, for each bit, there's roughly a 50% chance that it's in exactly one of the strings.
And so what you mean by removing it is you don't need to add it back into the pool. So this is removed, this is removed, this is removed. But this gets added back because we remove shared overlaps, and this gets added back because we skipped it.
Yeah, so the things that are just blue and just red, we know these have the same sum. So we can use these as part of one thread and then use the other ones as part of the other thread. Mm-hmm. And then everything that we didn't use, well, we still have some subproblem that we have to solve, but in this case, n is now smaller. So n's about half as big. Okay. And we can keep doing this, and we know solutions exist because there are just tons of subsets and not that many sums. But we can keep doing this, and then each time we do it, n will get about half as big.
Okay, so now we have like kind of a logarithm trick to get us down to our n equals 25 case, and then use our n equals 25 solution to finish off the remaining string.
Yeah. One thing that you might be a little concerned about here is that I said there's like a 50% chance to remove each element, but they're not independent. So one example you might consider is like, what if one element is odd, but the rest of the elements are even?
So we have like a 7 and then like 4, 6, 8, 10. So all of these are even. This one is odd. And so now if we ever pick this element in one of the sets, it's entirely not possible to pick something disjoint from this that sums to that value.
Yeah, so like in this case, like 7 plus 4 plus 10 is equal to 7 plus 6 plus 8. But if the 7 is in one group, that means the sum's going to be odd. And if the 7's in the other group, or if the 7's not in that group, the sum's going to be even. So if two sums have the same value, that means either both of them or neither of them have the 7. So it's not necessarily true for every element there's a 50% chance of it getting deleted. But when you have a whole bunch of elements, it's like you can ignore some of the elements because it's just important that you delete a lot, not that you delete exactly half. Which is why this approach works when n is really big, but when n gets small, it becomes very sketchy and unreliable. Which is why for n's like less than 100, we use the previous idea that we talked about earlier.
Yeah, so we basically need to ensure that we're reducing the size of the array by some like constant factor on n, right? So if we make it 1/4 smaller n, we're still going to have, in terms of big O, a logarithm on the number of steps that we need to do, right?
Mm-hmm. Exactly.
Yeah, and so that's the idea. So even though we don't like have to remove exactly half of them, we can remove 1/4 of them. And if you work with the recurrence directly, you'll see that this also comes out to a logarithm.
And it turns out that since n gets like half as big each time, it's kind of like the argument that a segment tree only has order n nodes, not n log n nodes.
Mm-hmm.
It turns out that like the runtime is dominated when n is big. So it's really roughly just order 10 to the 7, not 10 to the 7 times log, which is an easy thing to.
Oh, right, because yeah, it's basically there's this algorithm called quick select that you may have seen, and the idea is you like here's your n elements, and then you take this half, and then you take this half here and this half here, but then we know that like if we take all of these elements over here and move them over, we'll see that all the work on it's basically dominated entirely by the top pass. Everything after that point is going to fit under it. So this is a constant factor of 2 more than linear. And then if we're not deleting exactly half, then it's going to just be a constant factor of like how deep this is. So you are going to do more work if you're only deleting 1/4 of the elements, but it's at most a constant factor more work.
So yeah, that'll let us solve the problem when n gets up to roughly like 1,000, because we can keep decreasing it, and then once n gets small enough that it becomes very sketchy for us to rely on the fact that these are independent events, then we can start using the n equals 25 case to repeatedly remove groups of 25. So that'll let us solve the problem up to n equals 1,000. And it turns out we can actually even solve it for n equals something bigger than 1,000, because like the birthday paradox argument is assuming that birthdays are uniformly distributed. But in practice, well, birthdays aren't uniformly distributed. Like people are more likely to be born on certain days than others, just in the real world. But these sums certainly aren't uniformly distributed, right? It's really, really unlikely for every element to be added together. And that's what would need to happen in order for your sum to be 2 times 10 to the 8. So like it's very unlikely that that number gets picked. And it's much more likely that about like 5 times 10 to the 7 gets picked. That's a pretty likely number. That means, I don't know, about half the numbers get picked. Each number is about half its max value. So that's a number that is very likely to get hit twice and is very unlikely to get hit like for something that's the sum of 0. The chance of that happening is like 1 and 2 to the n. So it's more of like a Gaussian distribution or a normal distribution.
Yeah, so let's get a new page and we can start talking about like why that is the case. So let's talk a little bit about why this isn't going to be uniformly distributed. So we have a bunch of strings that come out to a certain size, and remember we're completely picking them randomly between 1 and 0. So equal probability of one being chosen and the other one not being chosen. And so I just wanted to talk about a few probability things because I think some people might be interested in this. So instead of picking 1s and 0s, let's imagine we're picking uniformly from an interval between 1 and 0. And we wanted to basically just do the sum of these variables. So this is just a continuous probability at any given time. And if we take the sum of all these events, because remember expectation is linear, so this is a unit distribution that's completely uniform between 1 and 0, and we sum this, we end up getting a random variable. But what's very interesting is as you increase the length of this string, you get a very special distribution. And that distribution is called Irwin-Hall.
Just to be clear here, Matt, for each of these variables we're picking, are these doubles or integers?
Yeah, they're doubles. So they're just continuous real numbers. So I'm just sampling them from real valued space. But I just want to get across this probability idea. Sure. And so if we end up summing these values together, if we only have one string, it's actually going to be uniform. So if we end up drawing our axes here, and this ends up being up to 1, then this is the probability you'll see is uniform. But what ends up happening when n equals 2 and you sum them together, your probability distribution looks something like this, right? So the idea is it's very unlikely that you end up getting the highest value both times or the lowest value both times. What you end up getting in average is you end up getting something towards the middle. And if you look at the Irwin-Hall distribution as you basically as you get more and more samples, there's this theorem called the central limit theorem that says that as these probabilities go out to a certain amount, this distribution becomes Gaussian. And so this is what David was talking about when he was saying this distribution was close to Gaussian. There's another related distribution that's really cool that you can go read about on Wikipedia. So instead of taking the random variables over the sum, we just take the random variables over the average of these unit distributions. And this goes by a different name called the Bates distribution, which is also a very useful distribution, and they have very similar properties. But in this case, the Bates distribution is really interesting because the variance starts to narrow as you end up getting closer and closer to different values. But the problem here is in our problem, we were actually picking from a binary values. So we're picking 0 and 1 from this distribution for so equal probability of not picking something or picking something. And it turns out this also has a very close to Gaussian distribution. And the name of this distribution is called a Bernoulli distribution. So you can just read about these things in a probability textbook. And the last thing I wanted to say is let's give a little bit of intuition on why this distribution is Gaussian and not uniform when you do this kind of sampling. So think about all the bit strings that we have. Remember that you basically, the number of bits that are on, the number of ways you can do it is n choose k over 2 to the n. And so what you'll notice here is there's only one way we can turn everything off and get a sum of 0 if we were to sum everything. And then there's only one way that we can get a sum of the maximum sum. But there's a bunch of different ways that we can pretty evenly distribute the two halves. And so that's shown by this Gaussian distribution as you go out to a certain number of steps, because this is the one way that we can get a sum of completely 0. And this is the one way that we can maximize our sum. But the really high probability event that has a lot of different ways is when you end up making k nearly half of n. Most of your samples are going to fall into this space. And what we're basically claiming in this problem so far is because the probability is the worst case scenario is if it was uniformly distributed, right? Because then it would be even harder to have collisions. But the collisions are very likely going to occur in the meat of this Gaussian distribution, which is going to be pretty narrow because we have a Bernoulli distribution.
Exactly, yeah. So just with this intuition, you can think like, well, this answer probably works for bigger n than n equals 1,000, but it's a bit sketchy to rely on this, and it requires some pretty high-level mathematics to come up with anything formal. So I think it's probably easier to.
Yeah, bounding this with the probability distributions would be a big pain. But I think there is a way to do it.
If you're very into math, you can go for that. Otherwise, you can just trust in the heart of the cards here. But otherwise, we'll try a slightly different solution for when n is bigger, and then we can use that to actually bring n down to something below 1,000. This is kind of a separate idea, which will work for n all the way up to 100,000 or 200,000, but it'll only bring n down to just below 1,000.
Okay, so our strategy here is now we're going to try to come up with a trick to bring the solution for n equals 2 times 10 to the fifth down to the n equals 1,000 case, and now we have a solution to the n equals 1,000 case, and we can just apply it to solve the problem.
Exactly. So one thing we want to consider here is how many strings can there be if we know there are no two pairs of strings with the same sum? And the answer is, I guess, not that many. So if every pair of strings has some sum, we know the number of pigeonholes that we have is going to be 4 times 10 to the fifth, because each sum is between 2 and 4 times 10 to the fifth. So we have that many pigeonholes. And then if we have n strings, there are roughly n squared choices for the possible pairs that we can get. So like n choose 2. And we know n choose 2 has to be less than or equal to 4 times 10 to the fifth. So you can do some math here, and it turns out that it winds up being that n is going to be something less than 1,000. I don't know exactly what it is, but it's pretty clear if n equals 1,000, then n's too big.
Or n minus 1. Yeah, so you can just do some algebra here and solve for n, and then figure out like what it would bring the n down to end up having a solution here. Okay?
So if we can find out some way of making sure that every pair of numbers has a distinct sum, this will definitely get the n small enough that we can use our previous solution with no issues. So the question is, how do we do this? So we want to say anytime there are two different pairs of numbers that have the same sum, we want to remove these two pairs and then like add these to the two threads at the end. But we can decrease n by 4 if we find two pairs of numbers with the same sum. So first, like,
so
maybe
let's give an example of what you mean by like two pairs of numbers with the same sum. So you're thinking like 1 and 9 and like 3 and 7, right? And so
yeah,
this is one pair of numbers that we're going to put in the blue group, and this is one pair of the numbers we're going to put in the red group. And so this is what you mean by pairs of pairs.
Exactly. And then we can remove these now and decrease n by 4.
Right. So,
and of course, these don't have to be next to each other either. They can be anywhere.
Yeah, they can be distributed however you want. So you could have, just to give an example, and so here we have the pairs how I have them. So I could end up picking these, and then for the red, I could end up picking these. And then there can be gaps in between these. I just have to find these pairs that they sum together. And if I can find these pairs, then I can group them together and then just eliminate them from the solution.
Yep, exactly. So one approach we might want to do for this is like we could just do maybe an n squared for loop. And this is going to be too slow because we can't just do n squared, but we can talk about it a little bit more. So if we did an n squared for loop and then we said for each pair it's got some sum, we can put this sum in some lookup table, some big array, and say this sum is mapped to by this pair.
I see. So you do an inner for loop, outer for loop here. And we basically throw the pair into some table, and then basically see if we ever have a collision, then we just remove those two pairs, and then do something smart where we skip over it. But this is obviously too slow.
Yeah, so like this isn't going to work because, well, it's just pretty clearly n squared. So one thing we can do is say, as soon as something gets removed, we can not iterate over it anymore. So we can have, instead of like an array that we're iterating through, we can either do some sort of set, or we can do We can use like a Fenwick tree and then find the next thing that hasn't been removed and store like a 1 in some position if it's not removed, or a 0 if it is removed. So there are a bunch of ways of implementing it, but basically we want some sort of data structure where we can easily remove something from it and then iterate through the whole thing. Maybe even a linked list would work.
Yeah.
I guess that's kind of the classic, right? Linked list.
Yeah. Or you can do your logarithmic Fenwick tree because it's pretty fast and it's a lot shorter to code than a linked list. It's very, very low overhead. So this is the competitive programmer way of solving a problem when you don't want to use your classic algorithm data structures like linked list.
So yeah, that works. Although we still have a little bit of a concern. So it's possible that we add a whole bunch of pairs to our lookup table that all involve like the first number.
Right.
And then if we end up removing that first number later on, we ended up removing a whole bunch of pairs between that and something else, which we had to spend runtime making. So we made all these pairs, and then we remove all of these pairs all at once because they're now all invalidated because we can't use this number in a second pair of pairs. So we've invalidated a whole bunch of things, but we've only decreased the number of elements in our array by a constant, by 4. And that winds up making this break in some cases.
Okay.
So we have to find something better to do with that. And what we can do is, instead of doing the for loop in that position where we, like, the first loop iterates through the first position and then the inner loop iterates through everything after it, we can instead first brute force the delta and then brute force the first of the 2 elements.
So you're saying with the delta, so here's like a delta equals 1, so we just go over adjacent pairs and see to find stuff to remove. And so we could remove some stuff from here with the pairs that how we have them. So maybe we remove these 2 pairs. And so then on the next loop, we also have a delta. Maybe we remove a few more pairs than just that. And the next loop, we can use a delta of 1, where we're basically just like skipping over things modulo 2 in terms of how far we're skipping. And then let's say we don't remove anything from this. That next loop we can do modulo 3. So something like this. And then just keep doing this until we're out of pairs.
Exactly, yeah. So one thing that might be a little bit concerning here, we'll talk about why this approach is fast in just a minute. But one thing that might be concerning is some viewers might be wondering, how do we make sure we don't remove like AB and BC? Like, what if AB and BC have the same sum?
Oh, I see. So you're saying that
how do we know there isn't the same element that's used in both of the pairs we remove?
So something like this, and then we ended up wanting to remove it here and then removing it here.
Yeah, and obviously this isn't allowed because we can't use B twice.
Right.
We can only use it once in one thread. So in order to handle this, like, this is a case we have to watch out for. In order to handle this, we can start off by just removing all duplicates. So if A plus B equals B plus C, that means that A and C are the same value, and we can really easily just remove A and C from the beginning.
Right. So yeah, you just have the B's cancel like they did here, because we have A plus B equals B plus C. So these 2 sides cancel, and so they would have had to have been equal to have this work. And so then what we end up doing is we just remove all duplicates ahead of time. And that kind of helps us anyway, because if we do have 2 things that are the same, then we can put one in the blue group and one in the red group. And that's what you're thinking.
Yeah, exactly. So then we should probably talk about the runtime of that approach by first iterating through the delta between the 2 and then next iterating through by the start value. So yeah, what is the runtime of this? It might seem like maybe it's n squared, right? Because you have n different deltas, and then for each delta you have n different starting points. But it turns out we can bound it to something better. And the reason for that is we know that at any point in time, the total number of pairs that we have included in our DP, the total number of edges that we've added total, is at most 400,000, at most 4 times 10 to the 5th. So what that means is, like, every time we remove, or anytime we have more than 4 times 10 to the 5th edges, where an edge is just like a pair that we've added, Anytime we have more than that, then we're going to end up removing some pair
Hmm.
by the pigeonhole principle. And when we remove a pair, we know that all nodes or all of these numbers here have about the same number of edges. So we're removing the same number of edges every time, or we're removing like an equal proportion of the edges every time we remove a node. So in the beginning, we remove about 1 over n of the edges. And then after a bunch of steps, we're going to be removing up to n over n of the edges. So when there are n elements, the edges are distributed evenly. We remove like 1/n of them.
Yeah, so
And then,
let's talk a little bit about how this is a graph. So you're basically saying that the strings are nodes,
mhm.
and like the first pass through the delta, everything has degree 1 because we're going to add an edge because this is a considered pair, right? And
Yeah,
then
exactly.
in the second one, and so like even though we're adding things for like all the active nodes, they end up having the same degree at all times, is what you're saying, because of
Yeah,
this like weird order that we're doing. Because when we were doing it the other way, we ended up having one node having a ton of degree basically, and because it just has this really big degree, we're wasting a lot of computation by doing it in this order. If we end up throwing this node out at the very end, let's say.
exactly. And then we can stop ourselves from doing that by spreading things out more evenly. That way we can't ever waste our time too badly. Like we waste a little
Mm-hmm.
bit of our time, but it'll be moderated. I
Yeah.
guess also just you can also loop around here. It's a bit difficult to draw, but you can also
Oh yeah, yeah. You
do
can.
stuff under mod.
It's just like wrapping where this guy over here is actually this first element. Yeah. Yep.
Yeah.
So it's like modulo k, where k is your delta, basically.
So our total runtime is going to be equal to the total number of edges we add. And the question might be, um, how many edges do we remove at each step? Because if we end up removing a whole bunch of edges, then we might add a whole bunch. So initially, since we know the total number of edges in this graph is at most 400,000,
Mm-hmm.
that means any node we remove will remove 1 over n of the edges that are still there. Or I guess 400,000 over n.
So you're just like amortizing it over the number of nodes.
Yeah, because like the total degree is about 400,000, and then so each node has about 400,000 over n degree. And so this will be the cost of doing one removal. So the total runtime is like this over n plus this over n minus 1 plus this over n minus 2, all the way down to 400,000 over 1. Does it make sense where all this is coming from?
Yeah, yeah. And so then now we have this harmonic sum because we end up having the same number every single time. So this is going to bound very, very nicely due to the harmonic sum.
Yep. So this is like n log n, if I remember correctly.
Mm-hmm.
If we assume
Yeah.
n is
Yeah, so I guess we could rewrite
400,000.
this as like 2n, right?
Yeah, that might make more sense.
Yeah, because if we're going to bound it logarithmically.
All right, so yeah, by doing this, we're able to make sure that every pair has a different sum, which means we have at most like fewer than 1,000 elements. And then we can use the earlier solution we talked about with the birthday paradox stuff to bring our 1,000 down to 1,000 over 2. We keep going using that pattern until we have at most 100 elements. Once we have 100 elements, we can repeatedly take the first 25, keep removing from those until we have just 25 elements. And then once we have 25 elements, we can find our final solution. And each time we're adding to the two threads, building up some more and more complex solution at every step.
Yeah, and if our remaining set ever gets below k, then we can just quit at that point because we're allowed to throw away k elements, and k is the min of 25 and n minus 2. All right, so now that we're near the end of the episode, David, do you want to go through like what you were thinking when you were coming up with this problem and like where its place in HackerCup was?
Yeah, so I first came up with like the general idea for the problem, just with the idea of finding two disjoint subsets is actually just the same difficulty as finding two subsets with the same sum. And I thought about this actually like several years ago when I was just driving home from my internship, which was very far away from where I lived. But yeah, I came up with that idea, and I'm like, oh, that's a really cool, non-trivial observation, and I've never seen that in a problem before. Let's try and see if I can force that to be used. And then when we were coming up with problems for round 2 in Hacker Cup, we tested the problems we initially had. We thought maybe this is a little bit too easy. We're probably going to get, like, we were worried we might get over 500 people solving all of the problems, which wouldn't be very interesting for round 3 because only 500 people qualify. So we're like, okay, let's come up with something a bit harder, at the very least to keep it interesting for the top competitors. And we actually found out how to increase the bounds of this problem from the initial bounds of 30 all the way up to 1,000. And then one of my teammates who also works in Hacker Cup, Jacob, he came up with an idea which was separate but worked by doing the making sure each pair has a different sum idea. And combining all of these different solutions, we were able to come up with a nice way of getting it to work all the way up for the nice bounds of 200,000, which make it very clean and very similar to other competitive programming problems.
And so everyone that solved the problem in the contest solved it exactly the way we described in this video, right?
Well, yeah, it turns out that although there were lots of different steps, you actually can miss basically any one of the steps except for the interesting ones and still kind of get a correct solution. Because it ends up being really, really difficult to make data that breaks somebody's solution if you don't know what it is.
Right. Yeah, I don't envy you with like judging this problem at all because it seems like the data making just to try to like come up with ways that people could cheat to get around this problem and cheese the problem. There just seems to be like so many little like heuristics that could work pretty well. And just by the birthday paradox nature of this problem and partition problem having all these good approximations, it just seems like it would be such a hard task to make the data to break every single kind of solution.
It was tricky, and we were also bounded by the maximum data size because Hacker Cup's format's a bit different. You have to output all of your data and stuff. So we couldn't have that many very big cases, which meant we only had like a couple big cases we could work with. So that part was a little tricky. I know there were a couple people who had slightly interesting solutions. Ericto had one that was a bit interesting. He found elements that would like there was the thing we talked about earlier about if there's just one odd number in the array, that number is definitely not going to be part of it. So he did something where like he tried to identify the problematic numbers, like the 7 that we talked about earlier. And he was able to effectively do that well enough to pass the data. And then Tourist did something where his idea was very much optimized around just checking the first 25 or so. And then he was able to speed that up with some other optimizations. So there are lots of different approaches that worked. But a lot of them may have been difficult to prove the correctness of, but were very hard to break in practice, I think. And that's part of the reason we wanted this to be in round 2 rather than a later round where it could be deciding on like who goes to round finals. This way, if you come up with a cool idea, it's like congrats to you, you made it to round 3. But we didn't want it to like and ruin anybody's contest or something like that.
Yeah, I think that's a good decision. And it sounded like so round 2 was the t-shirt round, correct?
Yeah, so if you were able to get this one, you had a much better chance of getting a shirt.
Okay. But like you feel like everyone that got this problem also would have gotten a shirt based on the other problems they solved.
It seems very likely, yeah. If you're getting this problem, you probably are definitely good enough to get a shirt otherwise. So I don't think that was unfair. Also, you can get a shirt if you're in the top 2,000, even though you have to be in the top 500 to get to the round 3. So you don't necessarily need this problem to get a shirt either.
Yeah. I think all of that seemed like a good decision for the round and everything. And I'll definitely try to compete in Hacker Cup in a future year. I haven't competed in Hacker Cup for several years now, but it seems like a lot of fun, and I like the snappy new website for Hacker Cup in particular.
So I hope to see you on the scoreboard.
Yeah, get back into competitive programming shape, and kind of do some more contests. It will be a lot of fun. So yeah, thanks for coming on and sharing this problem. And I'm glad we could have a conversation about like all the little ins and outs of this one. I think there are lots of cool little tricks for every piece, and there's just like this really nice ad hoc nature to all of it. And so that's what makes this like a really beautiful, interesting problem. And I'm glad we could like go into it in depth in this video.
Yeah, thank you so much for having me.